Principles of immunochemical techniques used in clinical chemistry. In this lesson, we're going to talk about the application of antigen-antibody reaction in clinical chemistry, turbidimetric, nephelometric assays, gel diffusion, immune electrophoresis, FPIA or fluorescent polarization immunoassay, chemiluminescence immunoassay, and radioimmunoassay or RIA. Immunochemical methods are generally classified into two: particle methods and labeling methods or label methods. Under particle methods, we can use precipitation or light scattering, and under label method, it can either be non-competitive or competitive. So there are also subcategories under each: immunodiffusion, immunoelectrophoresis for precipitation, and nephelometry, turbidimetry for light scattering methods. For non-competitive, it's either one site or two sites, and heterogeneous or homogeneous for competitive assays. Let us first describe some terms. First is fluorescent immunoassay. So from the word fluorescence. So this is one which makes use of a label that emits low wavelength light, which can be excited to transmit higher energy light. For example, UV. UV has an energy of about 350 nanometers, and it can be transmitted at higher wavelength. Polarization. So this is when we align the light waves in one direction. We're using a special filter. The combination of these two, fluorescent polarization immunoassay, is also an FIA that is widely used. So what we know about antigen-antibody reaction is that they are specific. However, this kind of bond is non-covalent, so that means it is not as strong as a covalent bond, and it is reversible. Aside from that, there are other forces that may help in the interaction between antigen-antibody reaction because they are chemical. So there is hydrogen bonds, hydrophobic interactions, and van der Waals forces. Another thing is clonal variation. This means whether it is polyclonal or monoclonal. So whether the antibody is from the same source or they make use of several plasma cells to produce different types of antibodies. So this may lead to variation in the interaction, the strength of interaction between antigen and antibody molecule. Right, so when an antibody meets an antigen, there will be a formation of antigen-antibody complex, which is a reversible reaction. Once equilibrium is reached, the rate of forward reaction may be different from the reverse reaction. This is affinity of the antigen and the antibody. One of the ways to detect the presence of this antigen and antibody complex is through precipitation. This does not involve the use of a label, and most of the methods are qualitative, but of course there are also quantitative techniques. Solubility is an important factor in precipitation. Bigger antigens usually are less soluble and would be very much easier precipitated. Also, the charge, as you remember, the um, repulsion or attraction between charges, so that is another factor. Another one would be the temperature and the ionic strength or the concentration of the solvent that is used. We can see in this slide that precipitation, the maximum amount of precipitate, is achieved when there is equivalence. So that means that the amount of antigen and antibody are more or less proportional. If there is an excess of antigen or an excess of antibody, there may be a post-zone or a pro-zone phenomenon. Because most of the antigens are mainly proteins, it is possible to apply electrophoresis. And with the addition of the antibody, it will form a line of precipitate. We call this immunoelectrophoresis. When antigens and antibodies interact, there will be a formation of complexes, or they will lead to formation of precipitates. These precipitates can cause the light to scatter, and we can make use of some techniques like nephelometry and turbidimetry to measure the change in the absorbance. So we can see here an illustration when light is allowed to pass through and it approaches a solid object or a particle. So there will be reflection or refraction or light scattering effect. So the one that moves to the side would be the light scattering effect. One of the factors that can affect the light scattering effect is the size of the molecule. So we know that the larger the molecule, there will be higher chances of scattering and reflection. In this slide, we can see that this is the source of light on the left and this is the object, the bigger yellow object. So when light approaches this object, there will be light scattering effect which can go in different direction. The main difference between nephelometry and turbidimetry is the angle at which we do the measurement of absorbance. If we do it at 180 degrees or zero angle, then that is turbidimetry. But if you're going to take the um, absorbed light at 90-degree angle, so this is called nephelometry because that is scattered light. Aside from directly measuring the antigen-antibody complex that is formed during the reaction, we can also make use of labels that will make it much easier to detect the complexes, antigen and antibody complex, or even the free components. So this label does not necessarily distinguish between free and bound antigens. We'll talk more about these so-called free and bound components. The different labels that we can utilize in immunoassays should have the following characteristics. One, easily attached to the antigen or to the antibody. Two, it should be easily measured. Three, it does not interfere with the test or with the antigen-antibody reaction. And then lastly, it should be inexpensive or economical, and it should not be toxic. The first kind of label is radioisotopes. So we know isotopes being alternative forms of an element that possess a different atomic weight. So the advantages of using these isotopes as labels is that they are very flexible, they provide for sensitivity, and the size is big enough to be detected. But however, there are some disadvantages. It is toxic, so it is harmful to the body. The shelf life may be short depending on the isotope that is used. And another one would be the issue on disposal because it's not easily disposed of, and the hardware that is necessary for the detection of radioactivity. The second label that we can utilize in immunoassays are the enzymes. So for the advantages, it is diverse. That means it can be utilized in many different, the detection of many different substances. It can be amplified, so that means a small amount of enzyme label can generate large amount of products to be measured. Versatile, so again, that means it's applicable in many different substances. And then what else? For the disadvantages, it is labeled, so that's the opposite of stable. So it is easily destroyed by heat or ionic strength. And then the size, it's difficult because they are much larger. They are proteins, so they are much larger, more difficult to use them as labels to attach to the antigen or to the antibody. And then the last one is heterogeneity, which means that there may be an interference of the enzyme converting into other chemicals in the reaction. The third type of label are the fluorescent labels. So again, they have advantages and disadvantages. So the size is much smaller, easier to utilize as a label. It is highly specific and highly sensitive. On the other hand, it would require us to buy a special equipment in order to measure fluorescence, so hardware problem and background problem. And it provides for limited selection. So that means we can only use this for limited number of substances. For the last label, we have chemiluminescent labels. So they are smaller. So the size is an advantage, easy to use as a label, sensitive, and it provides a good signal. So that means it allows for easy detection of the substance being measured. However, for the disadvantages, we need to buy a special equipment in order to do this test or hardware problem, and because it is newly available, so this is a new technology, it would be the information that we have available is somehow still limited. We have here some questions about heterogeneous immunoassays. So the first question is, how do we know if it is heterogeneous? So if we see in the step the so-called separation of bound and free components or ligands, so that means it is heterogeneous. In order to do this, we need to add a technique, a step, which is washing or centrifugation. Is this advantageous over homogeneous assays? So the answer is yes. And the answer is, what are the advantage or advantages? Is that they provide better sensitivity and specificity. So heterogeneous assays are much better compared to homogeneous assays. What are examples of heterogeneous assays? So we can categorize them into competitive assays and non-competitive assays. So here are the main differences between these two. If it's competitive, there is an excess of an antigen. If it's non-competitive, there is an excess of antibody. So the competition here would be between the labeled antigen and the antigen, right? And then for the non-competitive, this involves the addition of a secondary labeled antibody. So the example given here would be RIA for competitive immunoassay and ELISA for non-competitive immunoassay. Sensitivity is the ability of the test to detect the presence of an antigen even if it's very small, also in a minute amount. So this sensitivity is determined by these two things. Number one, affinity of the antibody to the antigen. And number two is the detection limit of the label, depending on the label that we utilize. Now, what about homogeneous assays? So if we say that in heterogeneous, it requires separation. If there is no separation of bound and free components, so that means it is homogeneous. So is this also a good method? Yes. So the advantage offered by homogeneous assays, because there is no need for separation, it is much faster. And there is also adaptability. We can utilize this in many different situations. So virtually all homogeneous assays are one site, and virtually all homogeneous assays are competitive, and they are designed to detect small antigens. For example, therapeutic drugs or drugs of abuse, steroids, and peptide hormones. So those are the applications of homogeneous assay. In this slide, we can see the typical design of a homogeneous immunoassay. So this green object is the antigen. This antigen can be labeled. If you see there is a blue thing attached to the green thing, so that means it is labeled. But if it is alone without the label, so that means it is free or unlabeled antigen. So the antibody is the letter Y. Okay, and when this antibody binds to a labeled antigen, it produces no signal. But if this antibody interacts with a label, so that will cause a signal. So this is what is being detected. So there is no need to wash or separate the components anymore. So other approaches to homogeneous assays are fluorescence method, electrochemical method, enzyme methods, and enzyme channeling immunoassays. So those are just examples of homogeneous assays. So in this slide, we can see the so-called microparticle enzyme immunoassay or EIA, simply EIA. So we have here a solid phase, which is a glass fiber matrix. So we say solid phase. It is something where the antibody is attached or the antigen is attached to. So in this case, the antibody, there are two antibodies here. The first antibody, the white antibodies, are attached on to the matrix. After that, the big green thing is the antigen. So this big green thing may represent hormones or drugs or substances that we want to measure. So this antigen will bind to the antibody that is coating the surface of the glass matrix. And then after that, we're going to add an enzyme. So this antibody is attached to this enzyme. And then what will happen is that there will be attachment. So this is a double antibody technique. The first antibody, the white one, then there is a green antigen, and then the yellow antibody. So this is a sandwich assay or a double antibody technique. Now, since we are making use of an enzyme here, we need to add a substrate. When we add a substrate, it will lead to a chemical reaction and it will show itself in the production of a particular color. So there is a colored product, which can be measured using spectrophotometer, or it can simply be measured detected using our eyes. Competitive RIA, example for antigen. Right. So remember that in radioimmunoassays, there are three components. The first component would be the antigen. So this antigen is the substance that you want to measure. It can be a hormone, it can be a substance, any substance like drugs, any chemical substance. And then the antibody that is specific to that antigen. And then thirdly, the labeled antigen or the labeled antibody. So in this case, a little limited amount of reagent antibody is added to bind to reagent labeled antigen. So in this case, there will be a competition of this patient's antigen and the labeled antigen for the reagent antibody. And but this antibody is limited. So that means there is not enough antibody that can react to both the labeled antigen and the patient's antigen. Right. So prior to the test, these are the components. We have the antibody and we have the labeled antigen plus the second antigen, which is the sample, the patient sample. So the sample contains the second antigen. This is during the test. So what will happen? So these antigens, both labeled and unlabeled, will compete for the antibody. In this case, there will be formation of the bound component. When we say bound component, that is the antibody and the antigen are combined, and the free component, so that means the excess, in this case, excess antigen. This excess antigen can be the patient's antigen or the labeled antigen. So that is why we say that there is competition, competitive RIA. So after the reaction, so after we allow the antigen and the antibody to interact, the next step is to measure the bound to the unbound component. And this is done first by separating the bound from the unbound components. And that is done by washing or by centrifugation or by adding adsorbing agents. And then we can measure the uh, gamma or the beta radiation. This is inversely proportional to the amount of the patient's antigen from the system. And this is what we make use of in the measurement of patients' antigen against viral vitamins, hormones, and even viral antigens like hepatitis. This is a very sensitive test if done quantitatively. So the next one is solid phase non-competitive BRIA or immunoradiometric assay. So antibody detection is done by immobilizing the antigen, incubating the antibody with the sample, and then adding another antibody, so another sandwich assay, and the amount of labeled antibody is measured. This is a quantitative test. So we can see here, this is the solid phase. So the solid phase can be like latex particle. It can be the surface of the test tube or something similar. And then the antigen is attached to this solid phase, which is immobilized. And then we add in the patient's sample that contains the antibody. This will bind to the antigen, and we will add another antibody which will attach itself to this complex, particularly in the patient's antibody, which is labeled. The second antibody is labeled, which will allow us to measure the substance. So because this is radioimmunoassay, so the label is radioactive substance. So this can be utilized in the detection of antibodies like anti-HBsAg or maybe some hormones, for example, HCG, human chorionic gonadotrophin. Right. So next is chemiluminescent labels. So labels like acrydium or luminol is converted to a luminescent product when an oxidizing agent like peroxide is added. This will emit high energy radiation for a short period of time and can be detected using a device called a luminometer. So we can see here the reaction, the patient's antigen. This is the substance that we want to measure. And then we add peroxidase labeled antibody. It will form a complex, antigen-antibody complex. And then what after that, we will add luminol, which is the chemical, the luminescent chemical. In the presence of this peroxidase will produce this luminous substance, light-emitting substance, which can be measured using a luminometer. So this is a luminometer. It's very similar to the appearance of your spectrophotometer, except that what it measures is the intensity of light produced during the chemical reaction. In this slide, we can see the so-called electrochemiluminescence immunoassay, so or the ELEXIS system. Right, so the label that is added to the antibody is an ion, for example, iron, which can be reduced when reducing agents are added, which can cause the energy to be emitted. So this is a new technology, so we don't expect there will be many applications at this time. The next one is FPIA, or fluorescent polarization immunoassay. So in this assay, the antigen is labeled with fluorescein. That is a compound that can be detected at a very low concentration. So that makes it a very sensitive method. So two things are measured here, both fluorescent light and polarization. This fluorescent labeled complex rotates slowly and can be detected under polarized light. At the same time, the amount is inversely related to the concentration of the patient's antigen concentration. So polarization is used to measure the emission from the fluorescent labeled antigen bound to the antibody from the free fluorescent labeled antigen. Free fluorescent labeled antigen rotates quickly since it is smaller, so it emits less polarized light. It may be measured as a depolarization, and its concentration relates directly to the concentration of the antigen. So this can be utilized in the measurement of hormones and drugs in patients' sample. And some of this has already replaced RIA, or radioimmunoassay. So that is the last slide for this presentation. So those are the immunochemical methods for detection of substances in clinical chemistry. Thank you for watching this video and for listening.